It's determine the characteristic impedance and propagation velocity for the twin lead transmission line of problem 2.2, assuming R equals G equals 0. And then what separation is required between these wires to achieve a 75 ohm impedance?
All right, so this is twin lead. And problem 2.2, do they give anything else?
Yeah, so it gives all of the R prime, L prime, G prime, and C prime. So
this is problem 2.2?
2-2.
Yeah.
All right, hold on.
2-2 in the
Calculate the distributed parameters of 1 megahertz for twin lead consisting of AWG 26 copper conductor with center separation. All right, for this one, he provides formulas for it in the text where you can get L and C. Go with me on that? I'm going to show you a trick here. Now, this comes later on, but I'll just show you this. Anytime we have a transmission line, a constant cross section, remember transmission line, the electromagnetic and the magnetic fields are perpendicular to each other and the direction of propagation. Let me try to make sure you understand this. So if I just had a coaxial cable like such, and try to give you an idea, this is a coax cable. Here we would have current I that would go down the center conductor and it would return on the outer conductor. The outer conductor is usually just a woven aluminum type foil on a lot of the stuff that you run into. Y'all with me on this guy? Somebody has taken apart a coax cable in some way, shape, or form. You know what I'm talking about. From personal experience. You've seen it, right? Now there's one thing that's very important. The same amount of current going down is coming back. It's called a differential current. It means the net current flowing through any perpendicular surface right here is 0. Y'all follow me? It's called a differential current. Now what happens inside here is you're going to get an electric field that will be radially outward, like such. This would be an E field. It will be at a snapshot in time, regardless of where you are on the wire, it will be either pointing out or pointing in, and the field lines themselves will be, or the electric field will be strongest near the inner core and then fall off. But this comes later in the course. Y'all with me on this? The current flowing down here would also cause a magnetic field, and the magnetic field would be in the azimuthal direction. Y'all with me on this class? Now, both the electric field and the magnetic field are perpendicular to each other at every single point, and they're also perpendicular to the direction of power flow. Power is flowing down the conductor. Y'all follow me now? I mean, it's down the transmission line. We'll get to that later. But E and H are perpendicular to that. That makes a transmission line. All right, you follow me on that so far? Now, if you have a transmission line, not a waveguide. Waveguide is something we're going to get to later on that literally confines the bouncing of electromagnetic waves. But you can have an electric field and H field, a component of it, in the direction of propagation. You're going to get to see this. For transmission lines, you can, for TEM mode. Clear on this class? Now, if you have a transmission line, there's one really neat thing. That I think when Whitmer's book, he brings it out, he just hints at it. Doesn't say it the way it should be said, in my opinion. If you have a transmission line, then this is true. And you have a transmission line where the parameters don't change versus distance down the line. So that means that mu and H, the actual permittivity and permeability, and this is terms that you're not familiar with. You all know what permittivity is? Dielectric constant. All right, that, and magnetically it's called permeability of the material that serves as the insulator. If they don't change, then this is always true. The inductance per unit meter, it's per unit meter times the capacitance per unit meter will be equal to mu times epsilon. Now, mu is the permeability, if we haven't even started talking about, and epsilon is the permittivity or dielectric constant. Y'all with me? So if you know the inductance per meter, you can get the capacitance per meter, and vice versa, assuming you know these parameters. Now that twin lead they're talking about has air as the dielectric, doesn't it?
Yes.
All right, so both of these for the twin lead will be mu 0 epsilon 0. Now, I don't know if you remember mu 0 and epsilon 0. When I had to take physics, the third physics course that I took, before I got into electrical engineering courses like EMAG, they did a whole bunch of stuff with the curl of H equation and the curl of E, and you learned Maxwell's equations, and you had to know these things very, very well because of the nature of the problems. And also because of one other thing, and I'm going to put it here. The velocity of light, c, is approximately 3 times 10 to the 8th meters per second, and it happens to be equal to 1 over the square root of mu naught epsilon naught. I don't know if you remember that, but that's how they actually obtain the velocity of the speed of light mathematically from Maxwell's 2 laws, even before the Michelson-Morley experiment, before they had very accurate means of measurement. They had mu and epsilon, but they didn't. Measuring the speed of light is no small feat, I'll tell you that right now. They did do it accurately, but it takes time. Anyway, back to this. Yeah?
I'm sorry, I was.
Okay, back to this. Now, if you have twin lead line, he gave you formulas for this, but if you have twin lead line, it's like this. You got a line, and you get a line, like such. And their separation distance, D, between the centers, is a constant. Each one of these wires will have some radius, R equals A, call it. I'm sorry for the sloppiness of this. I'm trying to work through this kind of quickly. But y'all follow me on this, people? All right. Now the formulas to this really have to do with the capacitance per unit meter here and the inductance per unit meter here. I haven't covered this in the course, you're about to. To get this, we can do this very easily because we can find out if we put a given charge per unit meter on this line, an opposite charge per unit meter on this line. We can find the electric field that we develop here. We integrate the electric field between the surface of one conductor to the other. We get the voltage. Once we have the voltage, we know that C times V is equal to charge. I don't know if you remember that. Q is equal to CV. Mm-hmm. So you can determine the actual value of C. I'm not going to do that. I'm just going to tell you what the formula is. In the book, he gives you what? The C per meter for this. If you take a look at this, there's going to be an epsilon naught, because epsilon relative is 1 for this. Then there'll be a natural log, right, that appears. And actually, the way he does this, I'm thinking about inductance, his formula will be this over pi times natural log of D over A, I think. I don't know if this is the formula he has. Can anybody confirm that?
I think it was pi epsilon over the.
Oh, was it pi on top?
Inverse cosh or something like that.
Oh, he had that one. Oh, never mind.
Yes.
All right, he's going to have a formula for that.
I think that's what I written down.
You don't have, I figured you could just look that up in the book. Let me see what that is.
It's, I got it right here.
Okay, what is the formula?
It's 2 pi epsilon over natural log B over A.
2 pi epsilon over natural log of
B over A.
D.
B.
B? Is B the separation distance?
Yes. I think that's for coax.
That's the coax cable, yeah.
Oh, okay.
Now this is twin lead. This is going to be pi, and I think it is pi epsilon up top.
Inverse cosh.
Yeah.
Yeah, it's the hyperbolic cosine.
Yeah, cosh of, and then it's going to be separation distance D over A, isn't it?
2A.
Over 2A. Okay, so that's diameter. Anyway, these formulas are these formulas come later in the course. We're just using this to get C, that's all. So if you do that for this problem, you're going to get a value, right? What value do you get? We're going to do this kind of quickly from here on. Just give it to me. If you got a calculator, go ahead and do it. It's good to do these problems, and if you can, bring your calculators and do the problems here. I'll tell you why. There are some odd little things you're going to find out about your calculator that you don't know until you actually experience it. And on the first exam, actually the first couple of quizzes actually get into some of these We're gonna use hyperbolic functions. You'll find out that you don't know how to use them, and if you wait until the day of the test or the quiz, and then I don't know what to do. You know, Dr. Baginski, I don't know. And it's like, it's too late. You're responsible to know how to use your calculators. Just remember that. That's why I tell people to bring them in class and do it. What did you get for this, anyone? Just this value for C prime. Anybody? I mean, you got calculators, right? The values are there, correct? Just punch them out. Did anybody do this problem at all? Besides the person who asked the question?
I didn't do it this way.
Well, I'm going to do it this way for a very important reason. I want to first make sure you understand that mu epsilon business is equal to LC. When you understand that, it saves a lot of work. And the second thing is, here he says R and G are 0, so it's lossless. And we'll get to that in a second. Anyway, what do you get for it? Anyone? Epsilon, you don't know epsilon. Epsilon naught is equal to about 8.854 times 10 to the minus 12. The units are farads per meter in case you want to know. And I might as well put up mu naught is equal to 4 pi times 10 to the minus 7th henries per meter. These are two well-known constants that we'll be using all the time. You've seen them before. You probably don't use them enough yet to have them burned in your brain like the speed of light and stuff, but you will. You have hyperbolic Koch, don't you, on your calculator?
Yes, sir.
All right.
What were the values for D and A?
D is a separation distance center to center, and so for twin lead, he'll give you that parameter. And A is the radius. Huh? Oh, he has, it's American wire gauge. They'll have that. Unfortunately, it's usually in inches or microns. I'll tell you what. I'm gonna, when you get this, give it to me. But the nice thing is, once you have that, to get L prime, which you also want, L prime right here is just gonna be mu epsilon over C prime. Right there. Now, once you have that, you all follow my reasoning. If I can get this, I surely can get this, knowing that mu and epsilon are just mu naught epsilon naught. Now, once I have that, if I want to get the characteristic impedance, and this is important now, y'all follow me the way I'm doing this. I'm assuming I can nail that. It's a transmission line, therefore I can nail this per meter. You with me, class? So if I have these two things, now what is the actual characteristic impedance, Z? Z naught. Well, technically it's the square root of what? R prime plus J omega L prime over G prime plus J omega C prime, right? That's the technical definition, including losses. Do y'all follow me? It's stated in the problem both R and G are 0. So I make R and G 0 by erasing them. And one thing that's very apparent is what? The J omegas cancel for a lossless case. Follow me? So when that happens, I'm really left with just the square root of L prime over C prime. And here's the beautiful thing. Now I'm going to go ahead and put these in here, right? And you're going to see something neat happen. So that's the square root of L prime, which is this, mu naught epsilon naught over C prime, and it's divided by C prime. And C prime here is going to be here. Now I've done this for a reason this way. So I put L prime in terms of the C prime here, first one, and then I divide it by C prime. What do you see happening? Just take a careful look. You see how I have C prime squared, but I take the square root of it, don't I? Can you all see this? That means the result is this. This is just square root of mu naught epsilon naught, right? Divided by C prime, isn't it, class? Everybody with me? there's one thing the bell should go off in your head. What about square root of mu naught epsilon naught? Every time you see that, what comes to mind? Speed of light. In this case, it's 1 over the speed of light. Y'all follow me? So now I can just take this and replace it by this. And in fact, this will be the characteristic impedance. Now, did anybody get the value of C prime there?
8.678 picofarads per meter, I believe.
678?
Yes, sir.
678 times 10 to the minus 12. That's fine. That would be farads per meter, but this is fine, 8.678. Now, if you take that, take 1 over the speed of light, which is about 3 times 10 to the 8th, times that, take 1 over it and tell me what you get. And that should be the characteristic impedance that's given in the answer. If we didn't mess this up, if we didn't fudge too badly. Is that right? Class? That problem? You have the answers. Is that correct? It is correct?
No.
No, I mean, is the answer, do the solutions have that?
No.
What do they have?
470.
470. So we want, there is something a little amiss, and I'm going to bet in Dr. Whitmore's statement of the problem in 2.
I don't think in the original statement of the problem, I think he wasn't lossless. I think in the one note you said assume it's lossless. I think in that problem though, he had a resistance
It
value.
won't matter though, because he said, he wants to see if it had losses, there would be an imaginary part. There is none to this, is there? It's just strict real, isn't it, class? For the answer?
Yeah. The answer is strict real, yes.
If it's strict real, it has to be losses. Okay, it's that simple. Now, this is American wire gauge 26, and the problem separated by 1 centimeter was the separation. Did you use 1 centimeter in your calculation?
I believe so.
And then you got the radius of 8WG from the back of the book?
Yeah, I believe it was 15.94 mil.
But mil is what?
And then I converted that should be, that's like a millionth of an inch, I believe.
Yeah, but the problem is this,
It's multiplied.
it's 2.54
2.54
centimeters an inch, right? And if you did the conversions right?
I think I did my conversion right. I might have gotten the factor wrong. I did 2.54 times 10 to the negative 5. Should it be positive?
No, that's for meters, that's correct.
Okay.
That's correct. If you're going meters, you're right. Anyway, I'm gonna say that somewhere in those details, there was something not right, or Whitmore's wrong, either one. Now, what the other thing is, and I think somebody alluded to this fact, that he stated what the values of L and C were, didn't he, in problem 2?
Mm-hmm.
All right, so now I'm gonna go back to his statement. What did he say his value of C was?
7.1 picofarads.
Which is different than ours. There's the difference. So if you use his 7.1 times 10 to the minus 12 farads per meter here, and then stick that in to this, take 1 over his number and divide by C, you'll get the right answer here. Go ahead and do it. Prove it to yourself and prove it to me. What do you get?
469.
Is that what he has?
470.
All right. I'm gonna tell you one thing about Whitmore. So he's a real stickler, I think. Dr. Whitmore's a great guy, brilliant guy. He does not like a number with 30 different digits after the decimal point. It's if you have 2.00001, it is 2. Do y'all follow me on this? He rounds things, and it's a fair statement to do that. So if he had 470, it's fine. Okay, but that's how you do that problem. Thank you very much. My real thing I wanted to do here is underscore the fact that if you have any type of true transmission line, if you have L, you have C, and if you have L or C, you also have the characteristic impedance. And it's very easy to get if they're losses, okay? That's a very important thing to know. There is no mystery there. Okay. Any other questions? I'm sorry I spent that much on it. Okay. All right. Now, next, I've got a few things to cover today. And hopefully, next class, I'd like you to bring Smith charts. I'll mail you. How many know what a Smith chart is? Okay, did you use them in laboratory work? How do you know about Smith charts?
My roommate took EMAG already.
We used them in work.
I mean, in physics, did you have them? I didn't think you'd get them in physics, but. All right, well, Smith charts are something, I mailed you a Smith chart that you can print off and bring your copy of it. It's a fairly good, high-resolution one, and we use this. Smith charts do us all sorts of favors. The biggest favor is they reduce the amount of work we need to do. So, but before we get to Smith charts, last time, I think the last thing I was talking about was actually power. And did I go through dB with you guys last time?
Briefly.
I talked about dB microvolt, or did I talk about microvolts or dBm?
Yeah.
And then I talked about the dB volts and dB microvolts microvolts or dB microamps. Let me just start from that point. It'll be good. So in general, when we talk about dB, right? dB is equal to 10 times the log of any quantity related to power. Anything related to power. Or a dB is equal to 20 times the log of anything related to voltage, or 20 times the log of anything related to current. Now current and voltage is what? Volts. Current is amps, right? And by the way, it could be volts per meter, that would be electric field. It could be amps per meter, that would be an H field. In any case, if you're dealing with either voltage or current, there is a 20 on the front of the log. If you're dealing with power, there's a 10. Now, some people will wonder why. Well, power is always related to what? V squared, right? Isn't it related to the voltage squared or current squared? Think about that. You put V squared here. If you take the log of V squared, the 2 comes out in front, it becomes 20. Do you all see this? These two, the dB difference in a signal, if it's power or voltage, will be the same. And you'll see that in a bit more clear. Now, the thing that becomes very common to do is use dB normalized to some value. So we talk about dBm, and that's going to be 10 times the log of the power, and the power would be in watts, over 10 to the minus 3. The minus 3 is 1 milliwatt, and the M there is milli, so it's saying that it's normalizing the actual power value, or dividing by 1 milliwatt. That would be dBm. When you talk about dB microvolts, this is used a lot in EMC world. Now you have 20 times the log of the voltage over 10 to the minus 6. Because a microvolt is 10 to the minus 6 volts. Do y'all follow me on the reasoning? From there on, it becomes intuitive. The only other one that's really common is dB microamps, and that's 20 times the log of I over 10 to the minus 6. Those are the three. I think I gave some examples. In radar, I went through the same thing yesterday. I don't remember what I covered in your class versus the radar class. So if I gave you a signal of power, and it was 1 watt, what would the power be in dBm? These are my little quiz things. I'll ask something like this on a quiz for just a point. What would it be? Just look at the formula. What do I have to do? It's 10 times the log. That's a log base 10. Remember, it's not ln. You got to be careful, because how many know on MATLAB, if you type log of something, it's actually the natural log? How many know that? You'll find out the hard way. Log on MATLAB is not log base 10. If you want a log base 10, you have to put log 10 parentheses, then the value. Y'all follow me? And I hate that kind of stuff because I assume certain things are consistent throughout the domains I work, and that's not one of them. On your calculators, they probably have LN, don't they, because they're engineering calculators? Well, there are calculators that have LOG and then LOG10. And I don't know if the old HPs had that or not, but anyway, I'm glad that your calculators don't. So anyway, it would be this times what? The log of 1 watt over 10 to the minus 3. Believe it or not, there are people that unless you do this and force yourself to think through it, they'll mess this up. You don't need a calculator for this, right? Isn't 1 over 10 to the minus 3 10 to the third? You all agree with that? So I can say this is equal to 10 times log base 10 of 10 to the third. Okay, how do you do that just in your head? Well, y'all see if you take the log of a to the b can come out front, right? Y'all with me? So that means 3 can come out front, make that 30, get rid of that. And what is log of 10? 1, right? Log base 10 of 10 is 1. If it's ln, you'll get a different answer. But y'all follow me? And so therefore, since that's 1, it's just 30 dBm. Now, next, I always do this. What if the power is equal to 10 to the minus 12th watts? What is it? This one I'm not going to work it. Just look at it. What would it be? All right. Reason through it. It would be what? 10, that's out in front. LOG of 10 to the minus 12 over 10 to the minus 3, correct? That's 10 to the minus 9, isn't it, class? So the minus 9 comes out in front, right? That means I get minus 90, right? Times the log of 10. Log of 10 is 1 minus 90. Do y'all follow me? Okay. I'm just doing those 2 examples. I could go through with one with voltage. Suppose I had a voltage of 1 volt. What is it in dB microvolts, just to finish this thought? If we have a voltage V equals 1 volt, class? So you're gonna have what, 10, right? Or not 10, 20, right? 20 times the log base 10 of 1 over 10 to the minus 6. 1 over 10 to the minus 6 is 10 to the 6, correct, class? So I'm just gonna put 10 to the 6. And what's that? Just by looking. I take the 6 out in front, right? 2 times 6 is 12, 120 dB microvolts. And that's the way this stuff works. So don't let it scare you. Now, next, I want to talk to you about how they actually go about dealing with one other factor, the relationship between the attenuation constant alpha and the actual attenuation in dB per meter. And I'm going to give you an example. This is a little something that can be confusing to people, so I want to just make sure it's not too confusing for you. Okay. Now, think back to the last lecture. Do y'all remember how I found out when I had power flow, P is a function of Z down the transmission line, I said it was equal to 1/2 the real part of V times I conjugated. Do y'all remember this, class? I went through that, I developed something. When all was said and done, you had this thing, you had basically V naught squared over the magnitude of Z naught divided by 2 here, because there was 1/2, or I can put a 1 there too. And then you had a cosine of the angle associated with the characteristic impedance Z naught. Do y'all remember that? That cosine value came in there? How many do? Not a lot of you, but we worked through that. This is a formula. And then you had something where you had e to the minus 2 alpha z. Do you remember that part?
Yeah.
All right. So we worked through this, and this is the relationship of power that would flow down a transmission line at any point z. This is P of z. Now the truth is this entire quantity here out in front is a constant. So I might as well just make it easy on myself, and I can say P of z is some P naught. That P naught is just a constant. That's all that junk. Do y'all follow me? Whatever it amounts to is P naught, or P0, e to the minus 2 alpha z. And this is the power that would flow down the line. Now there's some things that you have natural questions for. Well, where do you get V naught from and things? These will be answered shortly, but I'm just telling you, this will be the form it takes. And it is for a wave traveling in the plus z direction. So this is, we're ignoring any wave in the minus z at this point. Try to get down to the interesting points about it. When we have that, there's something that's very important. In transmission lines, for any transmission line, any coax cable you get, if you buy it from, or if you use it for anything from Spectrum or anything like that, Cox Cable or Verizon, they look for the attenuation in dB per meter, follow me, or dB per 100 meters. That's important. And here's where we get a relationship between alpha, which is in Napiers per meter. Alpha has the units of Napiers per meter. But we're going to get alpha in dB per meter. Now I want you to follow me on this. So if I take a look at something and I have a given sectional line, I'm just going to do this in a simple block form, like so. This is a transmission. And I know that this thing is exactly 1 meter long. All right? And I'm going to say that here is 0, z equals 0, and here is 1, and this will be the z direction. So this is z equals 0, z equals 1 meter. And at this point, I have something, I have a waveform and it's just entering, so the power entering here will be P0. Now this makes intuitive sense. I'm saying that's how much power is right here. Okay. Go ahead, you can ask me.
I was just.
This is a meter.
Oh, okay.
Not a very good meter, but it was meant to be a meter. You all follow me? It's just a 1 meter chunk. I got P naught here. That means right here at this point, since it's attenuating, it would be P naught e to the minus 2 alpha would be the power coming out. You all follow me? Now, does that make sense to everybody? Now, if we want to find out how many dB per meter difference it would be, we would say, in terms of dB, it would be 10 times the log base 10 of the output power, which is P naught e to the minus 2 alpha. Z is 1, that's the reason I didn't add it right here, right? That's the reason I chose 1. Divided by just P0. Do y'all follow me? That's the ratio of the amount of power left at 1 meter versus what entered. Y'all follow me on this? The rest is attenuated or dissipated. And if you look at this then, and I'm doing this, I'm not doing it the way he does it. Y'all see the P0s canceled, right? Now remember, this is going to be the attenuation that this has, and it would be in dB per meter. Remember that. I took the ratio of the output power to the input power for a 1 meter section. So it is a difference in dB per meter. Y'all follow me? All right, when you look here, what happens? I have 10 times the log, this is the base 10 log, of e to the minus 2 alpha, right? Now, I'm going to do something here that I think should make sense. I'm going to take this exponent and take it out in front. So that means I have minus 20 alpha times the log base 10 of e. And again, this would be in dB per meter. Now, you can do this, if you have your calculators, do this with me. This is really what? This is going to be minus 20 times log of e, that's the natural log, times alpha. Go ahead and take 20 times natural log of e. You should get 8.686, but go ahead and do it. Did you get that?
Yes, sir.
How many got that? Do it in your calculator, convince yourself. Take 20 times natural log of e. That's log base 10, remember that. Did you get 8.68? He did.
Yeah.
You did? Okay. So that's minus 8.68, and this is alpha, which is in Napier's per meter, is equal to alpha in dB per meter. Now this is the thing. Here, if I have alpha, this is in Napier's per meter. If I multiply that by 8.686 actually, then I get the attenuation in dB per meters. That's the relationship. And sometimes people get a little angst about that. But remember, if attenuation is given in dB per meter, that's this side. If you want alpha, you have to divide this quantity by 8.686. Follow me, class? And in his book, he states it explicitly that that alpha times 8.686 is equal to alpha that's alpha in Napier's per meter. That would translate to alpha in terms of dB per meter. Can you follow me? If you do a few problems, you'll see the relationship easy. All right, I wanted to cover that. Next, after that, now we get into terminated transmission lines. And if you have a book, I encourage people to bring their books. You have electronic copies these days, but if you bring your books, this is going to be section 2.4, and I'm going to do this in a way that I think is most appropriate for you guys, for you to actually understand it. So, a terminated transmission line is actually a line where you put a load on it. It's like it appears in the real world. And when you deal with that, this is going to be a terminated transmission line. So now I have a transmission line, and I have a load, some ZL. All right, the transmission line has some characteristic impedance Z0. Something else I have to do. I've got this one still to go to, but it's starting to fade on me.
You go.
Not green.
Oh, what color do you want? You want red, blue?
Dark black.
Dark black, got it.
Just toss it. All right, thank you. I owe you. Stop. I know this class already. All right, when you have something like this, you need a reference, so we're gonna use this as the z-axis right here. And this is a trick, and it saves some math. We always place the load at z equals 0, so call this z equals 0. All right, now the transmission line has a given length, L. All right, and this is the input to it, but for now, just go with me on this one, all right? We can say that, yeah, there's a voltage source here that's gonna have some V naught, and it's gonna cause waves to go down and back. You all follow me?
Yes.
Now, according to the electromagnetic equations we developed, we know that V of Z will have the form V naught plus e to the minus gamma Z plus V naught minus e to the gamma Z. That was for the voltage. And likewise, the current on that line at any point Z will be some V0 plus over Z naught times e to the minus gamma Z. But this point is a minus. It's important you underscore that. It's because the relationship to V0 minus to I0 minus. There's a minus sign there, and then it's V0 minus over Z0, and it's e to the gamma Z. Now those are the equations for both voltage and current at any point Z in the line. You're just gonna have to take that by faith. We developed them, but that's what they are, mathematically. Now, something as engineers we always talk about, if you can measure both voltage and current, voltage across and current through a device, we use that all the time. It's called impedance. So now we create something that we call the impedance of the line. Call it Z for impedance of Z. It's a ratio of V of Z over I of Z. All we're doing is saying if we're at a given point, Z in the line, anywhere, and I didn't show the twin conductors here, but y'all follow me, I'm just trying to show you it's a transmission. If you're at any point Z, you have a current that's measurable and a voltage difference that is measurable. The ratio of the voltage to the current at that point is called an impedance. It's given by this ratio, and that should be apparent to everybody. You know what impedance is, right? You've done a lot of stuff in there. Now, if you're at the load, if you're at Z is 0, so remember, I stuck the load at 0, right? If you're right there, well, I know what that impedance is. That's ZL, isn't it? The ratio to current to voltage at the load is the load, isn't it, class? By definition. It's also equal to V0 plus, take this equation, let Z be 0. So it's V0 plus V0 minus over V0 plus minus V0 minus, and it's this times Z naught. Let me just take a moment to explain why it's that way. If you look at this equation right here, take V over I, and then set Z equal to 0, right? Well, set Z equal to 0 first. It gets rid of all those exponential terms, doesn't it, class? Then when you take the ratio of V to I, V0 plus V0 plus plus V0 minus, divided by V0 plus minus V0 minus, and the Z naught flips, so it comes up top. You all see it? Now we talk about something that's real important, and that is something called the reflection coefficient of the load. Or really, yeah, this is going to be the reflection coefficient of the load. And we use the term gamma sub L. Gamma is always a reflection coefficient. Sub L just indicates it's the reflection coefficient at the load, where the load is attached. And that is the ratio, if you look at this. If I take a look at reflection, let me just define reflection coefficient in general. This is the general definition, is going to be V0 minus over V0 plus, but it can be at different points. So it's really, there's going to be something where these two may vary versus position. just go along with that for now. I'll try to expound on it in a second. So when I talk about gamma L at the load, it's really the ratio of V, and let me do it this way so you can see it better. I'm gonna do it right here. I wanna just let you follow me right here. Y'all agree that this is true right there, right? All right, now, don't write this down yet, just listen. I'm gonna go ahead and I'm gonna divide everything on top and bottom by V0 plus. Just listen to me, all right? So I get a 1 here. And then I get V0 minus over V0 plus. Y'all follow me on that? That's gonna be gamma. Gamma right there. That's the reflection coefficient at the load. Here I get V0 plus, right? Over V0 plus or 1. And then this is minus gamma. This is actually at the load. And this is equal to ZL. Do y'all follow me? Now, I can manipulate this, and I know I'm about out of time. I can get gamma L in terms of ZL and Z0. Do y'all follow me how I could do that? Don't write it down, just watch. Sure, I could divide this by Z0, right? Then I would multiply by 1 minus gamma L on this side, right? And then I would group terms of gamma L on one side and everything else on the other. When I'm all done with that, because I got about a minute left, you would get the reflection coefficient at the load would be equal to, write this down, ZL minus Z0 over ZL plus Z0. And that is the reflection coefficient that is very important. This is the reflection coefficient at the load or of the load. Now the truth is, that's really a ratio, I mean, that right there is important, but there's reflection coefficients at any point down the line that we'll talk about. This is real important when we use this. Now, I have, is it 12:50 ready? All right, I'm gonna have you read this section on terminated transmission lines. And then, since Friday is coming up, let's see, we didn't have a class Monday. You all have your books yet? Okay, what we'll do is have a quiz. It'll be on the homework I give today and last 2 homeworks, but it's more or less focused on the actual characteristic impedance of a line and how you get the relationship between that and the intrinsic parameters like R, L, G and C, and maybe some with power, but the problems I give you are going to be represented. Every quiz I give is based largely on the last 2 to 3 homeworks, usually the last 2. Follow me? So you'll know if you can do the quiz material, if you know the homework and you understand it, then you'll be able to do the quiz. It'll be the last 10 minutes of class. And are there any questions? Now, I think we got a class coming in, but I'm not sure. If you want to ask me questions now, it's fine. If you got any more questions for me, until I get thrown out of you, or I can go up to my office. But up here it's better because there's a full board to work with. Anything? I'm sorry I didn't have more time to finish